meine Damen und Herren, liebe Kolleginnen und Kollegen, es ist mir eine große Freude, Sie zu den 51. Wolfgang-Pauli-Vorlesungen begrüßen zu dürfen. Die Wolfgang-Pauli-Vorlesungen sind dem Andenken an den großen theoretischen Physiker und Nobelpreisträger Wolfgang Pauli gewidmet, der von 1928 bis zu seinem Tode im Jahr 1958 als Professor für theoretische Physik an der ETH Zürich wirkte. Pauli ist insbesondere für seine Entdeckung des Elektronenspins, des nach ihm benannten Ausschlussprinzips sowie seiner Voraussage der Existenz von Neutrinos berühmt. Die Wolfgang-Pauli-Vorlesungen sind abwechslungsweise den Gebieten der Physik, Mathematik und Biologie gewidmet. Die erste Wolfgang-Pauli-Vorlesung wurde 1962 von dem Physiker und späteren Nobelpreisträger Max Delbrück zum biologischen Thema Molekulargenetik gehalten. Seitdem haben eine Reihe bedeutender Wissenschaftler im Rahmen dieser Vorlesungsreihe moderne Forschungsthemen einem breiten Publikum nahegebracht. Die diesjährigen Wolfgang-Pauli-Vorlesungen sind der Mathematik gewidmet und es ist mir eine große Freude, Ingrid Daubechies von der Duke University in Durham, United States of America, willkommen zu heißen. Sie wird uns darüber berichten, welche wichtige Rolle die Mathematik für Aspekte des modernen Lebens, zum Beispiel für die Übertragung großer Datenmengen, spielt. Darf ich nun das Wort meinem Kollegen Marc Burger vom Departement Mathematik weitergeben, der Ingrid Daubechies genauer vorstellen wird.
Thank you. So it is a pleasure to extend a warm welcome to the Pauli Lectures 2015 in Mathematics. Our speaker this year is Ingrid Daubechies. She's native from Belgium and obtained her PhD in 1980 in theoretical physics for research in quantum mechanics at the Vrije Universiteit Brussels. In 1984, she received the Louis Ampin Prize in physics, awarded once every 5 years to a Belgian scientist on the basis of work done before the age of 29. She was then promoted to a research professor in physics at the same institution. In 1985, she began working on wavelets and joined 1987 the technical staff of AT&T Laboratories in New Jersey, where she worked on signal processing. It is around this time that Ingrid Daubechies developed a new theory of compactly supported wavelets and soon after introduced wavelet-based techniques to represent two-dimensional images. These Daubechies wavelets have found applications in a wide range of fields. In medicine, they are used in electrocardiograms and magnetic resonance imaging. In engineering, their use include analyzing the airflow around the wing of an airplane or the path of electrically charged gases in a nuclear reactor. And currently, her work found applications in art history, where image analysis can be used to distinguish an artist's brushstroke. In 1994, she was appointed full professor at the Department of Mathematics and the program in Applied and Computational Mathematics of Princeton University, the first woman to obtain this position. Since 2011, she is James Buchanan Duke Professor of Mathematics at Duke University in North Carolina. One of her most outstanding contributions is in the field of image processing, where her computational techniques and wavelet bases have been incorporated in the JPEG 2000 standard for image compression. Ingrid Daubechies' achievements have been honored with many awards. To cite just a few: the MacArthur Fellowship in 1992, the Steele Prize for Mathematical Exposition in 1994 for her book 10 Lectures on Wavelets, the US National Academy of Sciences Medal in Mathematics in 2000, and in 2011, the Benjamin Franklin Medal for Electrical Engineering. In 2011, Ingrid became the first woman president of the International Mathematical Union. During her 4-year tenure, she initiated graduate fellowship programs rooted in developing countries with the aim of planting the seeds of lively local mathematical cultures. Now I'm happy to leave the floor to Ingrid Daubechies, who will talk about how to find mathematics in art.
It's a a great pleasure as well as a great honor for me to be here and give these lectures, especially since Wolfgang Pauli was always one of my heroes. So I feel very touched. Okay, mathematics helping art history and conservation. It's really something in which I feel that, yes, we have helped, but they also have helped us finding very interesting and challenging problems. In the second half of my presentation, I will talk about work in which I've been involved myself, and in particular work that is in collaboration with the North Carolina Museum of Art. And collaborators there will be some of my students and collaborators at Duke, the people at the curators and the conservators at the North Carolina Museum of Art, as well as a Dutch artist about whom I will tell you more. But first, I'm going to start with two examples of work by other mathematicians who helped art history and art conservation. The first one is work done by Massimo Fornaziere. He worked on the reconstruction of frescoes in the Eremitani Church in Padua, in Italy. So the Eremitani Church in Padua had fantastic frescoes by Mantegna, which were destroyed in a bombing in the Second World War. Near the end of the Second World War, it was Allied bombing that mistook the church for a military target, and after that, the frescoes were this kind of rubble. Actually, here on this picture, you see that the bottom frescoes are still there. Well, they were the only ones that survived because prior to the bombing, they were in very bad state, the only ones that were really in bad state because of water damage, and so they had been removed from the church, and they were in a conservator atelier, and that's why they survived. The other ones were reduced to this rubble. So all this rubble was collected in many boxes, and in 1944, and they were kept. And every so often, art conservators would open the boxes and try to puzzle some pieces together, and would give up and close them up again. And in '92, all these fragments were collected, and that had been collected were cleaned, stabilized, and catalogued, because the hope was that by then there might be algorithms that were powerful enough to actually do this automatically, rather than having to do it by hand, which they had figured out in the 50 years that had gone on in the meantime, would be an impossible task. And the work, Massimo Fornaziere, who was then still a graduate student, proposed a method. So here you see these fragments. They're very tiny. They're a couple of square centimeters. They were a couple of square centimeters large, and they were all numbered uniquely on the back. And so all this was catalogued. And Massimo Fornaziere came up with a solution that made everything possible. So it's really, as I showed you, the fragments were very small, and they had no context. I mean, so yes, there were features on there. You saw. I mean, what can we see here? We can see parallel lines. We can see maybe here is something a little bit more interesting. I mean, what's that? Is that the eyes of a little alien? I mean, no, certainly not. But I mean, so there was really no context. You didn't even know what you were seeing, and all these fragments were in unknown positions, in an unknown orientation. So. And the surface of origin was much larger than the fragments that they actually had, the area of the fragments that they had. There were very few contiguous fragments. So what did Massimo propose, which actually made the difference and made this possible? Well, let's first think, once these images are catalogued and digitized, what does a digital image consist of? Well, a digital image on your computer screen consists of little points, little pixels, which are more or less bright, and on a color screen, of course, they're colored. But for the method that Massimo was going to use, he just worked in gray level, for a reason you'll see very soon. So they're points distributed on a rectangular surface, and we then give them a number between 0 and 255 for 8-bit quantization, where 0 corresponds to all black, 255 to all white, and then all the numbers in between, the 254 numbers in between, are what we in mathematics have as shades of gray. I mean, others have only 50, but so once you have your image in numbers, you have all these numbers, you can start comparing the sets of numbers between different images. So it seems very simple then. If you want to see whether two digital images are the same or very close, you just compare these tables of numbers, and if they are very similar, then you say, okay, this is probably the same image. They're identical, then it's the identical image. But it's not so easy, because yes, you might have the idea that you only need to compare. Yes, I forgot to tell you, when I showed you the fresco on the wall, we had color on the bottom with water damage, and above that we had a black and white picture. That's because in 1920, a photographer had made excellent quality photographs in black and white of these frescoes. And of course they're a little bit with a parallax, but that's easy to correct for. And so it was possible to make a print, I mean several prints that were glued together, of what a fresco must have been like, and put that on the floor at real size. So in principle, for every one of these little pieces, if you knew where it went, you could put this little color piece on top of the corresponding black and white piece, and it would have corresponded exactly. So what the hope was that you would digitize your little piece of the color thing, and you would then look for an identical piece in a digitization of. Now, it's not as easy, because the fragments, you have no idea of where, not only where they are, so you have to look over this enormous surface, but you also have to look over possible rotations. And you have to do all this efficiently. So here are, in fact, the same fragment of an image, but once it's in normal position, and then I have rotated it by a certain angle. And you see the numbers look completely different. So, and if you hadn't chosen yet a different angle, the numbers would still have been different. So digitization, of course, is different. I mean, because you always have a square here, and you rotate the image, well, now you're looking at what used to be a lopsided square before. So it's not that easy. But what Massimo proposed was something that was to use something that we know as circular harmonics. These are very special functions that have symmetries, and that you can use as elementary building blocks to represent images. So if you have an image, a little circular image, then you can, with these building blocks, write it as a superposition. Remember, all these things are arrays of numbers. So I can say I take 0.2 of this number, of this collection of numbers, and then all these numbers times 0.3, and then a 0.15, and so on, and add them up. And here's an example of the little image on the left, which is a very coarse version of the icon on the top left. So the image on the bottom right is a coarse version of the icon on the top left, and you see how I have built it up. It's being built up by more and more of these functions. And so what I'm showing you is, in this collection here, I'm showing you what I get after I take the first element, or the first two, or the first three, and so on, except I go much further than just 3. And you see how the image gets built up. So any image, any little circular image, can be built up by these building blocks. And now, each of these building blocks has such a nice symmetry that we know very well, if we rotate it by 25 degrees, what it will look like. It will look like a kind of multiple of itself with a coefficient here. And this one will have a different multiple, and so on. And if we have something that is these different combinations of the building blocks, then, well, we just have to multiply each of those by the corresponding number. So it makes it very easy to compute what a rotated version of the image looks like. And the decomposition can be done very fast. And so what Massimo proposed was on every segment, a colored fragment, on which there was a little circle that had content, you would take that little circle and decompose it in those building blocks. You would also look at locations of circles of possible different sizes, depending on what size you had on your building block, on your fragment, on the image, and look at their decomposition in harmonics. And then you would just compare these things with these different rotations, which were very easy to compute. So it made it searchable, even with those computers in the late 90s, which could only do as much as your smartphone can do now. But in late 90s, early 2000s, work cells were put together in Padua, where volunteers would come work for a few hours on the Mantegna project, and people would come and work on the data set. They would select one fragment from this enormous collection. They would then they would initiate the computation that would search for matches, and they would, from the top best matches, select that one that looked the best. So it was an enormous task. I mean, there were almost 81,000 fragments to be catalogued. And they were very small. And you see we have about 10% of the total area. This is an example of how this would work. So a fragment would be selected. This is one of those few cases where, in fact, there were contiguous fragments known, one of the few examples where art historians actually had managed to piece together something. So this circular piece here would then be compared by the computer programs with possible placements, and out would come possible matches, which would be visualized. And then the human operator would choose what was the best match. We're early 2000s, remember? I mean, machine learning was nowhere where it is now. And even now, there are many, many tasks where having a human make decisions in between makes it much easier than trying to do everything fully automatic. So yes, all these 81,000 fragments were placed. Look here. Here's another one. I mean, so, and they all worked out. It was, Massimo told me, it was amazing for the art historians. They would get the placement, they would go and say, yes, another one, I mean, and so on. So 81,000 times. Now, what can you do with that? Now, as Cesare Brandi, who is a famous art conservator, said, once you have a tiny fragment right, actually a good art conservator can use that to propagate information way further. And let's look at a few examples. Imagine that you have these fragments. I mean, you now know what the color is of this leather sandal. You know even this emblem here, that it has a different color. You know the color of the lens, of the tiles, of the toe. I mean, of his knee and the cap, where it ends here. So you can indeed propagate, and just imagine other examples. Here, I mean, all these color examples. Well, here there's not such a lot of color, but still the shading, and here you have these tassels and then this emblem. And so, okay, so this helped the art historians enormously already. But then Massimo went beyond this, and he realized that what they then do is when they have color information is propagated a little further, and then a little further, and a little further, and so on. We can do that mathematically as well. And so here you have another example. Imagine that I have this example of peppers, and I know color places in these big spots. And if you were to try to propagate, and we do that via a wavelet decomposition and by looking at the RGB version and saying that they have to have a similar support as the black, the gray, and the gray level picture. If you did it with that information, in fact, this is a very good propagation. It has missed something because it had no information to tell it that in this pepper color was going to change. It didn't look that way in the gray, and so it's not accurate. But the color information they have on the fresco is much more of this type. Little fragments that together make less area than what we have here, but that are sprinkled, peppered a little bit everywhere. And with that information, you can propagate. And in fact, that is what happened in Padua. He provided that information, and that then actually helped them in the propagation with their, of course, the tones were not exactly right. They knew a lot more about materials and so on. And so now if you go visit this chapel, you will see places where the fresco is partly restored as it would have been before. Other places where the fragments have been put in place, but nothing else is shown, just the gray and the gray level picture. Other places where they have the pieces in place, but they also restore color around it. But you can also see on a screen the virtual reconstruction as it would have been by only the mathematics methods. So that was a very beautiful piece of work for which Massimo deservedly got a big European prize. The next project, which is by somebody else than myself, on which I'd like to tell you, is by Rick Johnson, who is actually an electrical engineer and the person who got me, who convinced me to use image analysis tools for art conservation. He, in fact, did not work on image analysis himself, but he always was very interested in art. He spent a sabbatical in Europe about 8 years ago, got introduced to the conservators of the Van Gogh Museum in Amsterdam, and he actually said, look, you guys use a lot of science. You use X-rays, infrared photographs, reflectometry, and so on. Why don't you use image analysis? And they said, well, why would we? We are visually highly trained experts, and what would image analysis teach us that we can do? And it's true, they are visually extremely well trained. I mean, they notice things on these paintings that I mean, they notice, for instance, in Van Gogh paintings, Van Gogh was sometimes a bit sloppy with his paintings, and he would put them against the wall with newspaper in between when they were not completely dry. So they find traces of the newsprint of, so I mean, it's amazing. But he organized the first workshop where he convinced the Van Gogh Museum to make some data available, high-resolution data of their paintings, to some image analysis teams, and who then showed what they could do with them. And we have been having such workshops with an interval of about 18 months to 2 years ever since. The fifth one of them took place last year in Duke. We always try to hold them in museums or in art galleries, because we do want the art historians and the art conservators to come. We don't want to just talk to mathematicians. Tonight I'm talking to a different public. Well, although I hope there might be here some art historians who might come up with a new, or art conservators with a new challenge for me, but it has happened. Okay, so what he did was he realized in talking to the art conservators who were writing a new catalogue raisonné about Van Gogh. And a catalogue raisonné is one in which about each artwork that you show, you write everything, you know, everything. Every letter by the painter that discusses and so on, you cite. You try to bring everything together. One of the things that they do is they look at the thread count. They try to characterize completely the canvas on which it was painted. Now, how do they do this? I mean, you might think, well, you just turn the painting over. Well, in a very recent painting, indeed, that's how you would see the canvas on which the whole thing was painted. With Van Gogh it doesn't work, and with many old paintings it doesn't work, because oil paint is actually corrosive to fabric. And after a while the fabric starts disintegrating. And so most of the paintings in museums have been relined. That's to say, another piece of fabric has been attached permanently to the back. And so when you turn it over, you see the relining. You don't see the fabric. But if you look at an X-ray of the painting, this is an X-ray of a corner of the painting by Van Gogh that we just saw, you very clearly start seeing canvas lines. Now, why would canvas show up on an X-ray? X-rays go straight through material, fabric material. Well, what you see is not the canvas itself. What you see is the primer. You see, when a painting is prepared, a canvas prepared for painting, a prime layer is put on that makes the canvas much more rigid and also less absorbing of the paint, because otherwise you would put paint on it, it would be gone, and you don't really want that. So that primer, until very recently, would be something that had a lot of lead white in it. Lead shows up very well on X-rays. And of course, when you have canvas, you have valleys and mountains. And so in the valleys, you have a little bit more deposited than on the mountains. And so those differences in thicknesses are what you see on the X-rays. And you see it even better if you turn it over to a positive. I mean, you really can see the thread there. And so typically what conservators would do is they would look under a microscope, under a magnifying glass at the canvas, the X-rays of the canvas, of the painting, and they would count, 1, 2, and so on, and then another spot, until they got bored to tears. And so when Rick Johnson learned about that, he said, but you know, that is something that we can do automatically very easily. And we could do it everywhere. And I said, everywhere? I said, yes, everywhere. And so what you do is you just look at little pieces and you look at the Fourier transform and you look at where peaks are. I mean, and that tells you in what directions do I find a lot of oscillations, most pronouncedly, and so on. And so he would then, after he had the results, he would find ways of visualizing them. And what he did, what he's done here, this is, you see a fabric where, this is a painting where we have, I'll visualize yet another one. This is a painting where you have quite a lot of change in angles, because the fabric, of course, you have to put it over stretch it over a frame to paint. But before, when it's primed, it's very rigid. And if it gets primed while it still has some weave in it, then some wave in it, then that wave is frozen in and so on, and you cannot stretch that away after you put it on your frame. So you have here these changes in angle, and what these two visualizations, what Rick Johnson shows are deviations from average behavior. So he would look at the horizontal frequency, and he would have an average over the whole painting. And then he would have places where it was a little denser or a little less dense. And he would make that visible with a color, using rainbow colors. And similarly, vertically, whether you had an average where you were higher or lower than the average. And you could also do that with angle, because things are never, as in the left, exactly horizontal or exactly vertical. And so he would also show deviation from the horizontal or from the vertical angle. So he had 4 pictures of this information of the thread count and its angle for each painting. And what immediately became apparent, and which nobody had ever noticed because nobody had ever had the patience to look at all the little samples, was that this gave you a kind of fingerprint of the canvas. Here are 2 paintings that Van Gogh painted, and you see the same visualization for the vertical. This is a deviation of angle, I believe. It's very obvious that the fingerprint of the top one continues in the bottom one. And that's because Van Gogh, like many artists, would buy his canvas in bolts when it was much cheaper, and he would stretch it and put it on frames himself. And so these are, they coined a new name, roll mates. I mean, they came from the same roll. And this has led to, in the meantime, here are 6 paintings from Van Gogh's Arles period. And we now know that they fit on the roll like that. because one of their fingerprints lines up like this, and the other one lines up like that. And so it's very obvious that that's how they were. From the same roll, there's a painting by Gauguin, who was living with Van Gogh in Arles at that time. This is for Van Gogh, but there's a painting by Velázquez that had been de-attributed because it's not of the same quality as the masterworks of Velázquez, although it's a very nice painting. They said, well, it's probably from his studio. But examining the canvas made clear that it was a roll made with other masterworks by Velázquez, and Velázquez did not share his bolts of canvas with his students, so it's now reattributed. Okay, so I'm now coming to work in which I had a hand myself. The very first work we did for the Van Gogh Museum was in response to a challenge they gave us. When they gave us their data, they said, well, what shall we ask you to do? They said, well, can you quantify similarity in style? Can you quantify that this painting that Van Gogh admired has attributes of his own style? Can you, when we show you a forgery, see that indeed it is a different person painting this time Van Gogh? And so, yes, we could. And in fact, if you look on internet, Nova made a little television program about this. And so if you Google Nova, Van Gogh, art forgery, and so on, you probably can find that snippet. But I find that actually one of the least interesting projects we've worked on, because what's been really interesting is that whenever I've given a talk about things that I have done, and if there are art historians or art conservators in the audience, it can happen that they walk up to me and they say, you know, if you can do that, maybe you could do this. And so this was one of those projects. We call it Lady 6 millimeters Under. The art historians hate it when we call it that. So this is when this work was first done, not by us. We did something after the work by Joris Dick and Koen Janssen. It made a big stir. This is about 10 years ago, and it actually made the cover, as you see, of the Journal of Analytical Chemistry. Joris Dick and Koen Janssen are two chemical engineers. Koen Janssen works in material science. Joris Dick also works in art conservation, and they realized that they could, with the technique of X-ray fluorescence, get information on a painting that people were very interested in, but didn't know how to get to that information. So this is again a painting by Van Gogh. It's a study that he made in his Paris period. It's called A Patch of Grass. And it was known for a long time that if you turn this painting on its side, and then there's another painting underneath, you see here the X-ray, you see on the side, you see all the nails and so on in the frame. That's how you see it's an X-ray. And clearly you see here still remnants of the grass that we saw earlier. Here you see this big grass stem is something we see again here. But this painting is underneath, and that is not so surprising. Van Gogh was poor, and many of the paintings, about 30% of his paintings have something else underneath, because he would make studies, and when he felt he had learned out of the study what he wanted to learn, and since canvas was expensive, he would just put a new layer of primer over it and use it as a canvas again for new work. But this painting in particular was one people were interested in, because this painting underneath dates from his Nuenen period. Nuenen is a small village where he lived with his parents prior to going to Paris. And he was at that time making many portraits of local peasants in very dark conditions. And he was trying to see how, with a very restricted palette, a palette that had very few light colors, actually only one light color, Naples yellow, he could give an impression of color using lots of browns and some red and so on. And Vincent van Gogh all his life had a sustained correspondence with his brother Theo, and there's a letter of him from the Netherlands to Theo, then in Paris, in which he describes what he was trying to do, and he says, I'm sending you a painting in which I feel that I achieved particularly well what I'm trying to do. That letter has survived, but that painting was never found. And so because this is underneath a study made in Paris, people believed that that was that painting. And so that's why they were interested in seeing what it looked like, since he felt he had particularly well succeeded. Now, of course, in Paris he changed his style completely, so he no longer valued this earlier, and so it's not so surprising that he would paint over it. But people wanted to see. So what Joris Dick and Koen Janssen did is they analyzed this painting with, as I said, X-ray fluorescence. So what you do in X-ray fluorescence is you send high-energy X-rays on a little piece of material, and that ionizes the material, and then the electron falls back in 2 steps, one to a high state and then one to a lower state. And that second transition is one between 2 bound states of the element you're looking at, and so the wavelength, the energy difference, is characteristic for the element you're looking at. So if you do this and you look at the spectrum you get out, it tells you that you have a lot of this and very little of that and so on based on these wavelengths and their intensity. So this is what they got for this painting in antimony and in asbestos. Antimony was part of the Naples yellow that Van Gogh used then. Arsene, not asbestos, arsene, sorry, was part of the vermilion that he was using. And so indeed you see the lips coming out, and the tone of since it was the Naples yellow was the only clear color he was using then, so you see the face. So how did they do this? Well, now, because this technique has shown to be useful, people have made portable instruments with X-ray fluorescence for museums. But at that time, I mean, you don't meet high energy X-ray machines on the corner of the street. So they took the painting actually, and they somehow they got a grant to pay the very hefty insurance fee for doing that. They took the painting to a hospital in Amsterdam. Because hospitals have high energy X-ray sources because they use them to make short-lived radioactive materials that they use for medical tests. So, and it's customary, these short-lived materials have to, well, they live very shortly, so you just make them as you need them. And so, since you don't need them any minute of the day, there are times when the beam is not needed. And so typically there's a setup where the beam either serves its medical purpose or is diverted to another direction where physicists can use it for experiments. And so you can sign up for time there and so on. So they had signed up for time, and so when the beam was not in use for the medical people, it was directed at a small piece, a very small portion of the painting, where it would do its X-ray fluorescence, and then the beam was always in the same place, the painting would be moved, next one, and so on, and they would every time measure the spectrum. And that's what was put together here. But you see, there had been, I mean, since when the beam was needed, the whole contraption had to stop here, freeze in its steps, until the beam came back. And there had been a synchrony problem in doing that. And you see the trace of that here. I mean, the scanning was done zigzag like that, and you see here these dark pieces are where there's a big splat of paint on the top painting, which the X-rays couldn't get through, and so you have no information. But because there was a synchrony problem, you see that you have a zigzag tearing apart of things here. Now here it's very obvious, and but in fact it happens all over the painting, but with smaller amounts. So one problem was to rectify this, and Joris Dick had kind of rectified it by hand in Photoshop in order to correct here, but he did know that it happened a little bit everywhere. And also, in order from what I showed you to make this view, which made the cover of Analytical Chemistry, they had used the Naples yellow, they had put the red in, but then that was it. I mean, and already it was giving a much better impression of the painting. But he asked me, after I'd given a talk about the earlier work, about our work on forgery detection, could we do something with image analysis on this? And so we did several things. First of all, we did, on the data that we had before, we did a variational algorithm in order to correct for all these, to get something in which things were more aligned, iteratively. Then after we'd done that, we did in-painting on these blobs, because just like Massimo could propagate color, I mean, here again, look, it's painted. You can see where the strokes are. You can see how you would continue them. So you can in-paint what you don't have information for. And once you've done that, you can back out. You can use that in order, instead of the one with all these kind of little measles on them. And then finally, in order to integrate color, so we had a yellow, we had a red, but that doesn't give you everything. We were missing too many colors. But we did analysis of the paintings that Van Gogh made in the Nuenen period, all these portraits, and some are very low contrast, some are very high contrast, very bright, a very, very harsh contrast. But if you start making analysis of the color distribution, once you've removed that contrast, it turns out, and this must not even have been obvious to Van Gogh himself, that there's a systematics to the color distribution that you can back out. And so what we did is, since we had two colors, we then used that in order to complete. And so instead of what Joris Dick and Koen Janssen had put together, we got this. And so it really made her come to life much more. Okay, so I promised you I would talk also about work I'm doing with the North Carolina Museum of Art. So we are working and on an altarpiece by Giotto that is very, very famous and of which they are very proud. But it's preliminary work, and I'm going to tell you about a different altarpiece that they have. So this is much less famous, but still a pretty wonderful thing. I mean, it was in a much smaller church, a much less rich church at the time. It's an altarpiece that depicts the life of John the Evangelist, and of which the North Carolina Museum of Art has 3 panels. 3 more are in the Metropolitan Museum of Art. 1 is in Portland, 1 is in the Chicago Institute of Fine Arts, and 1 is missing. And it's been missing ever since. I mean, so with like many of these art pieces, you can look in the records when it was actually taken out of its church and taken apart and sold as pieces of art rather than as pieces for the devotion for which it originally was painted. And that 9th one is lost. I mean, we have no trace of it in the whole record. Bill Brown, who's the head conservator in Raleigh, North Carolina, told me that he had this dream of bringing together all these pieces, all these panels of that altarpiece together, since they were all in North America, in US museums, and it was much easier to do that within museums in one country than if it had to also cross borders. And that the other museums said, well, but it's not going to be complete anyway, because there's this missing one. And I then introduced him to Charlotte Kaspers. Now, Charlotte Kaspers is the person who the NOVA program, remember I told you that we had worked on trying to detect a copy from an original, and NOVA, in order to make television of this, had charged somebody who's a very gifted reconstruction expert of art to make a reconstruction of a Van Gogh painting, and then they had given us a scan of that and of 5 Van Gogh paintings, challenging us to pick out the one that was not by Van Gogh, even though it was done by this very gifted reconstruction. And we had, and actually you can see that in that snippet on NOVA. But so we had worked together. I told you she's an art reconstruction expert. Here you see her at work making a copy of one panel of the very famous altarpiece by Van Eyck in Ghent. She was commissioned to make the 3 copies of the same fragment, but to stop them at intermediate stages, so that people can see what the different layers are, the way of painting these in the exhibit. Here's another one where for a museum in Rotterdam, she actually stopped in preparing it every 5 millimeters. So the first 5 millimeters are the wood without anything. Then you have all the 5 layers of glue, and then the gesso. I mean, she only starts drawing here, she only starts painting here. I mean, these are all different layers, the bolus, the gilding, the polishing, and so on. So we had actually worked with her on not only the Nova Challenge, where we distinguished this one painting, but also I had commissioned her to make paintings, freehand paintings of little still lifes, and then using her training as a copier of brushstrokes to copy her own paintings, because we wanted a proof of concept. We were going to have the same artist, but one freehand and one is copying. You see, when she copies, she stabilizes her hand by giving it a support, and she's watching very carefully what she does and so on. So this is a very special training. And we could. I mean, I have this collection of old tchotchkes in my house now. We later commissioned her a series of paintings here, so if anybody wants to work on image analysis and make these data available, here we actually don't know for most of them which is the original and which is the copy. She has marked them on the back, the information is under seal in the art history department at Duke, and once we have come to a conclusion, we are trying out several analysis techniques in order to really, we're having lots of fun with it, we'll in public state what we say, and then the envelope will be opened. In any case, so she was commissioned by the North Carolina Museum of Art to paint this reconstruction for the missing panel. But how can you do reconstruction of a painting that you have never seen? Of course you can't. I mean, but what you can do is you can make a painting that, if it had been put in place of the original painting in the 14th century, would not have surprised people. You can make something that has the right scene, because this is life of a saint is very codified. This follows the Golden Legend, which is an earlier medieval book of describing the life of John the Evangelist, and so you know what scene should be there. He's converted, he's baptizing a famous person in that time. And if you study as art, you can see that the same kind of wooden, not perfectly formed movements are a little bit everywhere, and so you can make a scene that fits with that. And then here you see her working in different stages on that painting. This was all then documented by the Museum of Art in North Carolina. So they're going, when the exhibit is now going to take place, because they have this nice new panel completing the things. The other museums thought this was a really interesting project. They have agreed, and in the fall of 2016, about a year of now, this exhibit will take place in the North Carolina Museum of Art. So, and it will show not only the old paintings and the new one, it will also show this movie of how these things were made. I mean, with the techniques of the time. In that case, we actually have a manual for people who are making the paintings, so we know exactly how it should be done. And so this gold leaf was punched, so punches were made in the right shape, and here you see her punching it. Here, this is a detail of the finished painting. It's really gorgeous. And here, this doesn't do it justice, but you see how nice and bright. Doesn't do it justice because this polished gold is hard to see in a flat photograph like that. But it's so bright and shiny, and people will get a real impression of what it must have been in the 14th century, when these things, these yellow backgrounds were gold and shiny and polished and reflecting the candlelight and so on. And everything else will look incredibly dull in comparison. I mean, you see here, I mean, this is not a sharp picture, but you see the contrast. And so Bill Brown said, but how are we going to do this? I mean, and I said, but you know, mathematics can help. Because what we can do a detailed analysis of the old paintings, and that gives us an idea of the cracks. I mean, we're not going to make a physical model of how the wood split and so on, but we could do that, but that's much more work. But what we can do is look at the crack type of patterns and generate a crack pattern that would fit and so on. We can look at how the pigments have faded, and we can make a high-resolution printout of a virtually aged version of that panel. So they would have the new panel to show, and they would unite the thing with a printout, a high-resolution printout. But then obviously people will pay attention much more to the real old ones than to this print, but they can compare the print to the new. And so that's what will happen, actually. But we then realized that if we do all that, we can use that study to rejuvenate the old panels. And so, in fact, there will be, at the show, there will be the reunified altarpiece. There will be the new one with a case showing the materials in which it worked, with a little alcove showing a movie of how it was done. And then there will also be a presentation of how it must have been the whole thing when it was new, only virtual. And we will be able to make even a virtual little movie where your point of view changes and you see reflection of that gold as it must have been in real. And how can I do that, find these cracks and so on? Yes, we can, because in fact we have done it for a different application. And for the altarpiece in Ghent, there was a question about one panel. Well, there are many questions about it, but this one question. If you close it, then you have this Annunciation scene. Behind the Virgin there is this book. And if you look closely at the book, that's what you see, at this painting of the book. And so it looks like all horizontal and vertical lines to me, but which is not surprising. All these books look like that to me. Litera formata is something I cannot read. But experts could not read it either. And some of them said, well, of course not. I mean, it's not a book, it's a painting to pretend to be a book. And others said, but you know, Van Eyck was a real perfectionist. And there's this one group of words, Divisione Dei, that we can read. Maybe the whole thing was text. I said, yes, I mean. But I said, well, why don't you know? They say, well, we can't, it's too hard for us to think these cracks away. Our eyes are very good at things. You've all seen this optical thing where you see three little Pac-Man figures together and you infer the triangle that's shown by their open mouths. I mean, we are very good at inferring things, but we're very bad at thinking away cracks like this. Or thinking away, I mean, evolution has not prepared us for this. So, well, I said, well, maybe mathematics, maybe image processing can help. And indeed it could. And it was much harder than I thought, otherwise I might have not said anything. Because you see, all this brown is not uniform. I mean, but we managed. And so once we had found exactly which of these brown pixels were cracks, automatically, of course, because it's way too big to do by hand. You need to develop a method to do it automatically. And then you can start inpainting. And that's what's done here on the right. And to us, it looked just as illegible as before. But to the paleographers, it was a revelation. They said, oh my God, look at this. This is really part of an A, not of a U. This is, and so on. And they can now read 10 groups of words in this, sufficient to determine unambiguously that this is a piece of a text written by Thomas of Aquinas in the 12th century on the Annunciation. And it's an Annunciation panel. So they were very excited. This is a really big deal to them. So now, next we are going, now that we know, in the inpainting we hadn't used that this was a text. We had just used brushstroke and so on. Now that we know it's a text, we can use the places where the text is very clear, where the letters are clear, to do optical character recognition elsewhere and get more of the text. And they want to actually maybe even determine which copy of that book was used by Van Eyck, who must have had it at hand in order to make the painting. But so we know we can find cracks. And we know that the easiest way to find cracks is to look at X-rays of a painting. So I said, show me the X-rays of this Gissi panel. And they show it to me, and I say, but look at this horizontal and vertical stuff. That nonsense, what's that? isn't that a nuisance? They say, yes, it's a nuisance. It's the cradle. Cradle. Okay. So cradling is something that was done in the 19th and early part of the 20th century with paintings on wood panel. These wood panels were typically 1 inch to 1.5 inches thick, and when they were in their churches. And when they made their way into collections of rich people who could afford them, they were often planed on the back. Sometimes this was because they wanted to remove pieces of wood that had worm damage. Like the back of the Gissy panel actually shows worm damage. Or in other situations, it might be because there was some decayed wood from water damage. But in most cases, it was because they liked to hang these paintings flat on their wall, and these big wooden boards would work. And so they planed them down to a few millimeters, and then put, because now they had much less structural integrity, a cradle on the back, which is fixed members in the direction of the wood grain, and then tunneling through sliding wood members. And that's the cradle, and of course then when you take an X-ray, what you see is mostly the cradle. You see none of the subtleties in the brush stroking for which you really want the X-ray in the first place, or none of the... So a lot of the detail they were interested in was masked by this cradle. And again, it's very hard to think away the cradle. And so I said, well, they said, but it's okay, you know, we work on this whenever we have to prepare for publication. We work on this for a few days in Photoshop and remove lines line by line. And I said, maybe you wizards, maybe you can do something mathematically. I said, but if you have already done this, and it's just for this one exhibit, maybe it's not worth it. But a few months later, I was visiting the Prado and talking to the head conservator at the Prado, and I said, we've encountered this problem. I said, do you have this problem too? And she said, do I have this problem too? And she opens very Mediterranean. She starts opening drawers, she says, look, look, look. So it became clear that this was a very general problem, and so it might be worth developing an algorithm to do it. And so that's what we did. Was challenging because nothing is truly horizontal or vertical. Well, you have to find the right angles and so on. And then the shading is not quite uniform. But then, of course, I mean, once they realized that we were attacking this problem, they became a little bit greedy. I mean, they said, you know, what we really interested also in the wood grain. We were thinking that we would remove all the wood grain. But no, they said, we like to see the wood grain in the panel. We'd love to see the wood grain from the cradling gone. And well, I mean, we scratched our head, but that made it a very interesting problem, machine learning problem, because we were having to do this. We would have to learn this special texture. The horizontal texture is not so hard, but the difference in vertical texture from the cradling, from the panel alone, just from having examples of seeing the two together or only one. But it turned out that this was feasible. I mean, it was a really beautiful piece of work done by one of my graduate students. And here you see the results, comparing what Noel Cohn, the specialist in North Carolina Museum of Art, had done for this fragment, and what our algorithm does. And based on that, we then made the plan of trying to make this a piece of software that would be accessible and used by art conservators worldwide. Now what we had was a program in MATLAB. Now you can write anything you like in MATLAB. As long as it stays in MATLAB, it's completely useless to art conservation. They don't have MATLAB, which is expensive. They're not going to buy MATLAB. They're not going to learn MATLAB if you buy it for them. I mean, so what we did is we got a grant from an art foundation, And actually, we proposed this, and I got the most incredible letter that I've ever gotten when I got a grant from the grant person. He said, this was a very interesting proposal, a little bit out our comfort zone, he said. It made for the most interesting and lively board meeting I have. So there must have been people who said, oh, this is great, and others who said, are you crazy? Anyway, we got the grant, and this paid us money to actually make the MATLAB more robust, to port it to C++, and then to pay programmers, specialized programmers, to make a wrapper for it in Photoshop. And we make it available in open source, so on a website, we make available the MATLAB with documentation, the C++ documentation, the Photoshop wrapper, and all the papers we are writing about it. They explain the whole algorithm, the ideas behind it. And already conservators are telling us, couldn't you use it for this or that? Ideas we didn't do ourselves. We are an academic unit. We're not going to maintain this. This is not my dream in life, to maintain a piece of software for the rest of my life. But since we make everything available, we recommend to them that they contact local image processing, local applied mathematicians, who, with all the stuff we make available, will see what we did and maybe are interested in working with them. So we hope the whole thing will grow. And so this actually, on July 18th, we held a workshop where we invited local art conservators, well, not so local, I mean, there was one all the way from Chicago, to learn the thing, and they became beta testers for us, so they tried it and they told us about their crashes, and we made it more and more robust. And about a month ago, we put it online, so if you look at www.project-platypus.net, then you can actually download this software, and you see the platypus climbing out of his cradle. I mean, of course, platypuses have nothing to do with paintings, but it turned out to be a very good name because everybody remembers it afterwards, which is what you want from. So we're very excited about this as an open source project. We hope platypus will learn other things as well, and we already have projects in mind. And I think my time is up, and I should stop. Thank you.
Thank you very much. I guess we have time for one question, maybe? I don't need to put this on, no? It's on anyway, okay. So, we have time for a question. Yes?
Mm-hmm.
Please, Bert. Oh, thank you.
Well, that doesn't you.
So I come to this sort of get to this sort of question by the unicorn.
Unicorn, okay.
Where Chudovsky did much work about restoring
The tapestries.
tapestries. Did you have contact with him, or did you know about that? Or?
I don't know anything about work. I suppose he worked on the tapestries in the Metropolitan Museum in the cloisters.
In the cloisters,
Yes.
yes.
No, I didn't, and I should find out more about it. I mean, I have been in touch with lots of other people who do in-painting. We focus on things that we can do on images, so not necessarily, so we don't actually do material searches and so on, so there is much more sophisticated work that art conservators rely on than what we do. And, but on the other hand, we like it to be able for them to do something with stuff they already have, like the X-rays. They have that, and we can help them do things with it. And so we believe we have to establish a bit more credibility before they would take special pictures for us. But, so that's been our aim. But I'll find out about it. I'll contact him.
I think it would be
I've met him and I know him, but I don't know him well, but I know him. I know them, I mean, so I'll ask. Thank you.
There's a question here.
Concerning the frescoes, in your first example, if you do not have the original image, but just fragments, let's say, of a Babylonian tablet, is there any technique, or maybe even wavelet technique, that you could use to fit them together?
Okay, so the question is, if you, in the frescoes, the project was helped enormously by the fact that they had this black and white picture in which they could place a fragment. If you don't have such a picture and you just have the fragments, what could you do to put them together? I think if you only had, as in the frescoes, about 10% of the pieces and very few were contiguous, you could forget it. But unless you had examples like with cuneiform tablets, you might have others where you know certain formulaic things fit together and so on. If you have all the pieces and you can scan them with a high precision in 3D, then not only can you do it, but it has been done. And it has been done for cuneiform tablets, but it has been done also by a group in Heidelberg for temples in Cambodia. In Cambodia, these temples are built with a stone, the name escapes me. It's a kind of half-eroded sandstone that when you dig it up is actually soft. I mean, so it's peat-like. It's soft, and as you expose it to air, it becomes hard. And many of the temples have been built in that and then covered with things on which they make their beautiful bas-reliefs. These temples, when they were abandoned, were torn apart by vegetation, and you have all these pieces lying there. When they were dug up, these blocks, and soft, the people constructing the temples would use the fact that these blocks were still soft to kind of rub them together to make an irregular surface where each block would fit perfectly on the previous one. So all these blocks are unique in shape and they fit perfectly on the block underneath. So if you, I mean, and in fact to build together these temples, what they would do is they would put them together and they would say, does this fit, and so on. But these things weigh tons, so it's not so easy to play puzzle with them. So now they scan them, they do it all virtually, and things are numbered, and then they say exactly, put this block there, that block there, and so on, and it all fits. So that is done, and it's beautiful.
Okay, thank you. Some more question? Yeah, I wondered while I was listening to your talk, isn't this Archimedes palimpsest, in a sense, a problem in image analysis, which would have been for you?
Well, but people have worked on that with very sophisticated techniques, and I don't think we would be able to do anything more than what they have done. But that's a unicum. I mean, so it makes sense to develop things for just. You don't want to do an algorithm that's going to work on all the Archimedes palimpsests that you're still going to find, because you're not going to find another one ever. I mean, but we wanted to find things that would work on, as Laura Alba was saying, the Prado, all these things she had there. And in fact, since the thing has been online, it's been downloaded by over 30 museums worldwide. I mean, over 50 people, but of whom 30 museums. I mean, in Japan, in East and West Europe, in America, so we're very pleased. And this is before it has appeared in a journal on art history, so just word of mouth so far.
All right. Some other questions? Well, if not, then we thank Ingrid again for this extremely lively.